At this point, we've gone over the integral test error bounds, and now I want to talk about the alternating series test error bounds. So just as a reminder, when we have a series that has all positive terms, the partial sums always then grow, and then therefore they're increasing up toward the sum of the series when it converges. Consequently, because the error is defined as the true sum minus the approximation, in the case where we have all positive terms, that error will always be positive. This is not necessarily true for alternating series. Sometimes it can be positive, sometimes it can be negative. Consequently, to begin with, we're really just going to consider the size of the error. And by this, I still define error, E sub n, as s minus s sub n. But we're going to be interested at first in just trying to gauge a bound on how large that can be without worrying about the sign. So we'll talk about the absolute value of E sub n. And within this absolute value, we're defining that E sub n the same as we have so far. And importantly, it's the true sum minus the nth partial sum. Here we're just going to take the absolute value of that difference, which is also equal to the absolute value of the sum of a sub k starting at n plus 1 up to infinity. Notice the importance that these absolute value bars are very much on the outside of the summation. If it were on the inside, that would simply just make our series that was alternating one that has all positive terms. That's not what we're trying to do here. We want to consider the error exactly as it is, but in the end, we don't really care if it's the sum that's larger or the sum that's smaller. So suppose we have kind of a generic alternating series where I'm going to express my a sub k as negative 1 to the k plus 1 times b sub k. And so we're assuming here that b sub k is always positive. The sign is completely determined by that negative 1 to the k plus 1 term. And I also want to assume that this is a series that we can actually say converges by using the alternating series test. If that's true, we know that the size of the terms is decreasing. So I say the absolute value of my a sub k's, where again here I'm thinking of the entire term as a sub k. We're saying that the absolute value of a sub k decreases, or equivalently that b1 is greater than b2 is greater than b3, etc. So plotting the partial sums, first of all, because I happen to have one where the first term is positive when k is equal to 1, then the first partial sum is positive. And then because the terms themselves are decreasing in size, while I do get this oscillatory behavior for the partial sums, they're always going to remain in the first quadrant. So the first partial sum, I would then add a negative term to that to get the second partial sum, and then I'd add a positive term to that to get to the third, and so on. So we'd see this behavior where they would be all oscillating around what would look to be kind of a central location. And so what I'm indicating here with the dotted line would be an estimate of the true value of the sum of the series, which I'm calling S. Because the first term is positive, we can say here, as we see in this picture, that for the odd indexed partial sums, those are getting smaller as you increase the number of terms you're adding together. And in particular, the odd indexed ones would be decreasing toward the true sum of the series, whereas the opposite behavior is true. The even indexed partial sums are growing as you increase the number of terms that you add on, and those are going to increase toward the true sum of the series. Now, I will say we could draw a very similar picture with the assumption that the first term was negative. That would put all of our partial sums in the fourth quadrant, and it would change the direction of these inequalities. But we would still see this dichotomy of odd indexed partial sums versus even. Now, with that in mind, what I want to think about is how we can use this to find a bound on the error. So looking at the partial sums, or at least the plot of the partial sums, we can see that when I'm talking about the absolute value of the error, E sub n, again, that's the absolute value of the sum minus the nth partial sum. Let's pick a representative n here. So suppose I wanted to find E sub 5. Well, E sub 5 would be the vertical distance between the sum of the series and the fifth partial sum. So if I wanted to gauge e sub 5, we'd look at that. Now I'm putting the absolute value here because we see that that actually would be a negative difference here. And what I can confirm is that, actually let me change where I place that e sub 5. So what I would like to compare that to get our actual error bound statement, so this is E5, an absolute value, is let's look at the distance between S5 and the next partial sum. So again, in absolute value, I'm looking at the difference between subsequent partial sums. Certainly I can see in this picture that the blue line is longer than the red line, but let's kind of extrapolate here and imagine that I wasn't just looking at e sub 5. For any error term, we're going to track the distance from the partial sum to the dotted line, and that's always going to be smaller than the distance to move from that partial sum to the next partial sum, because we're always jumping over the dotted line. So what we're seeing here is that the true error, as I've written it here, is always smaller than the distance between the n plus first partial sum and the nth partial sum. And if you'll recall, we've seen earlier in the course that if I take a difference of subsequent partial sums, what's left over is just that extra term, in this case, a sub n plus 1. And here, I'm taking the absolute value, and I'll point out when we take the absolute value of a sub k for such an alternating sum, we lose the sign and we just get the size of the term. So I'll point out that alternatively, we could have expressed this as the b sub n plus 1. But I kind of like to write it as we have here to really emphasize that you should never get a negative when we're bounding the size of the error. So again, one kind of quick pause. The reason that we can reduce that is that we're taking the sum of the first n plus 1 terms, and we're subtracting from that the sum of the first n terms. Everything cancels except for this term, and that's what I've written there. So what does this mean about our error? Just to emphasize, what we get here is, this means that when we're using the alternating series test error bounds, we're going to be able to say that the size of the error, and using the nth partial sum to approximate the sum of the series, can be bounded above by the absolute value of the next term. And by next term, what I mean here is that we're cutting it off at the nth term in terms of our approximation. So next term just means the first term that we haven't included in our approximation, and here we're calling that a sub n plus 1. So to see this in practice, again, one thing I want to make clear is this notation. I hope that it'll be easier once you start using this. So in what I've written above, a sub k would represent this whole thing we have here, and b sub k would just represent 1 over k squared. So notice that as I was writing above, if you take the absolute value of what I'm calling a sub k, you would get this b sub k. So I almost find it easier to drop the b sub k and just kind of think of absolute value in the context of using this error. So here, find an upper bound on the magnitude of the error and approximating this series by its fifth partial sum. I'm going to emphasize magnitude here. When we see that, we're saying that we don't have to worry about whether that error is positive or negative. Later, we'll talk about how we could adjust this or use this to then determine a sign for the error in addition to that magnitude. But here, we're just looking at the size. So that allows me to use that boxed inequality exactly as it is. And the other thing I'm going to notice is this fifth partial sum. That tells me that I can assume n is 5 here. So this is really saying we need to bound e sub 5, or the absolute value of that. And according to our above result, that's bounded above by the absolute value of the sixth term. So I replace k with 6. And of course, the negative 1 to the k part is insignificant because we're taking the absolute value. But 6 squared is 36, so I get 1 over 36. This is just telling me how large in size the error could be at most, but not whether it's positive or negative. Much like we've seen with the integral test error bounds, another type of question we could ask here is how large should n be so that we can guarantee that our error in size is smaller than 1 over 100? Well, here we have some kind of desired level of accuracy, and we need to know how many terms we need to add in order for us to get close enough to the true sum. So just like we've done when we talked about the integral test error bounds, what we want to think about is we know that the error in absolute value is bounded above by, in this case, 1 over n plus 1 squared. Where did I get 1 over n plus 1 squared? Well, I took my absolute value of a sub k and I replaced k with n plus 1 because we're looking for that n plus first term. We need the absolute value of the error to be bounded above by 100. So putting these together, it suffices to find, I should say, n so that our known upper bound is smaller than our desired upper bound. So in this case, that 1 over n plus 1 quantity squared is smaller than 1 over 100. So by the transitive property, that will automatically ensure that the absolute value of e sub n is bounded above as well by 1 over 100. Here, I can cross multiply and say we need that 100 is less than n plus 1 squared. Here, I know that I'm going to have a positive n. There's no problem taking the square root of both sides and using this to simply say that the square root of 100, or 10, must be less than n plus 1. And now we can subtract 1 to say that we need n to be at least 9. And again, the direction of that inequality makes sense because as we increase n, the error is only going to get smaller. So needing to find kind of that cutoff where the error is small enough, then any n greater than that would work as well.